Greetings, everyone. I am Dr. Erwin Schrodinger of the University of Graz. I think you are familiar with my famous experiment, but just in case, let me give you a refresher. So first, we take an elephant, and then we put the elephant in a box. And then we seal the box. And then we expose the box to radiation. Now, elephants are extremely sensitive to radiation. And as a result, after having exposed the elephant to radiation, it might still be alive, and it might be dead. We don't know. Until we open the box, the elephant exists in an indefinite state, a state we call quantum superposition, where the elephant is both alive and it is dead, until we observe it. Now, of course, we're not conducting this experiment literally. This is a metaphor for what happens when you containerize a service like Postgres. But first, let's talk about why we'd want to put an elephant in the box to begin with. Why would you want to put an elephant in the box? Why would you want to put Postgres in a container? Well, first thing is, all the hip kids are doing it, right? I'm from Portland. We've got to be hipster, right? So putting Postgres in Docker, it's what we do. But more seriously, one of the questions is, why would you put anything in a box? So the question, why would you put something in a box? Security was one answer. But the bigger answer is, the reason why you put something in a box, well, a lot of people can't actually figure out why to put it in the box, and so they don't, right? They say, other things might be in a box, but let's not put PostgreSQL in a box. It's a bad idea. Instead, let's keep Postgres outside the box. Think outside the box. And there are a number of vendors right out here in the vendor hall who are happy to run your Postgres outside of a box for you. So, and this is what a lot of people are doing. I would say actually most people who are on a new cloud stack are doing is they're using an external service, whether it's Citus or Heroku or Microsoft or AWS or Google, to run their PostgreSQL and make it somebody else's problem. However, there's a very good reason to think about putting your Postgres in a box. And that reason is, same reason why you'd put anything in a box, which is portability. That is, you want to actually be able to take it places without worrying about it as an elephant. So we're going to box it up. Now, specifically when we're talking about this is, there's another trend in application development where one of the things is everything is moving towards continuous integration and continuous delivery. That is, rather than having 3-month release cycles or even 2-week release cycles, when commits come in and they get tested, then you deploy them to production. And this is the trend in mobile, and it's the trend in web services, and it's the trend in internal applications. I work at Red Hat, and we're actually redoing a lot of our internal stacks to be CI/CD based. And in a CI/CD environment, you need to be able to run everything at each stage of the environment. In development, you need to be able to run the full stack, including the database. In test, you need to be able to run the full stack, including the database. And if you've boxed PostgreSQL up, that is, put it in a container, this is much easier to do, because then you have your containerized version of Postgres that you can run in each environment. And that container image can follow the other container images from development to production. This is one of the reasons to do it. Another reason is this thing called orchestration. Now, orchestration is actually a thing sort of separate from containers, but it showed up with containers and really has become practical and widespread because of how easy containers make deployment. Now, the leading orchestration tool is Kubernetes, which is one of the things that I contribute to and work on. And the idea of container orchestration is you have a system that manages all your services in an abstract way on your cloud or on somebody else's cloud. And the thing is, if you've put your web servers and your application servers and your routers and your statistics and your monitoring and everything else into this container cloud, then you really want your database to be there as well. So that if you spin up a new instance of your application, again, that includes everything. You're not doing a completely separate orthogonal step in order to provision a database on RDS or on your own hardware or whatever. Plus, you gain some advantages through orchestration, things like service catalogs, where you can use relabeling and redirection in order to, say, for example, move something from test to prod, or decide where certain customers are going to connect. And more importantly, orchestration makes the deployment process really simple. You define stuff in static files in YAML or JSON, because that seems to be the templating for this generation of technology, and deploy your containers, and then the orchestration system takes care of where those actually end up in terms of physical machines. These are reasons why people want to put things on containers. Now, the other reason is, right now, orchestration, container orchestration-based hosting is a minority of hosting. There's a few platforms, Red Hat OpenShift, Google Container Engine, that sort of thing, in terms of public clouds. But the trend is that within 5-8 years, container orchestration is going to be the public cloud. So if you're going to want to continue running your stuff on the public cloud, then again you'll have a choice between the hosted database services or figuring out how to put PostgreSQL in a box so that you can run it in the public cloud as they will exist then. So reasons to box Postgres. Now, this would be a misleading presentation if I didn't talk about reasons not to box up Postgres. And there are a few things in the state of how things are now that are not working as well as we would like in a container orchestration environment. The biggest thing is if your Postgres is too big. So there are some issues with large databases, and I mean both large in terms of physical size and large in terms of the amount of system resources they consume within a containerized environment and within an orchestrated environment. One of them is some memory management issues that are specifically around Linux containers. And what this just has to do with is currently the only memory management we have for Linux containers is what's known as the out-of-memory killer. Out-of-memory manager is officially OOM, but it's known for everybody as the out-of-memory killer. And for a lot of you who are Postgres administrators, you have been used to disabling the OOM killer in various ways. And then when you go into a containerized environment, it comes back and you can't disable it. And so you need to figure out how to manage memory a different way, which is, again, not really a problem in small databases, but can be a real problem in large databases. Second thing is default orchestration setups, default schedulers, that sort of thing, are aimed at a situation where you have many services running on each physical node. And if you have large Postgres databases, you're really going to actually want to often isolate them to their own physical nodes because they're going to consume all of the hardware resources that individual node, or at least 50% of them. And that is going to push you into the direction of writing or modifying your own scheduler and doing a lot of extra configuration steps in order to make the orchestration system understand that this particular service needs to be isolated to its own nodes. That is Postgres. Another problem with large databases in a containerized environment is one of the ideas of a containerized environment is that individual instances of your service are disposable. Now, the way we handle that in the world of Postgres is via replication, right? Every time we decide, hey, this Postgres is on a machine that's way too crowded, or it's on a machine that is about to be decommissioned, and therefore I need to move it, what happens is you have a replica somewhere else, you kill that instance of Postgres, it fails over, and it brings up a new instance somewhere else. And you still have your Postgres service because the orchestration system redirects all of the connections to wherever the new instance is. However, that works great if your database is half a gigabyte. If your database is 6 terabytes, then the cost of spinning up an additional replica is quite high and also time consuming. So that can be a limitation with large things. Now, one of the other issues that we have, and I'm going to talk about it a little bit more, is observability, but we'll go into that. So right now, like if you were tomorrow going to get on GKE or OpenShift or on your own stuff or run Atomic Host and Kubernetes in your own individual cloud or whatever, and you wanted to run containerized Postgres, this is the sort of target use case where it makes a lot of sense and where it works really well. Small databases, and small is relative to your hardware capacity, obviously, where you can afford to have multiple replicas and you can spin up new replicas quickly, where you can actually work this into a test and deploy environment so you can gain that, and where you can maybe take advantage of offering self-service for developers. That is saying, hey, when your service is ready, you can deploy it, and that will include a PostgreSQL database to back the service. Because that's the whole advantage to make it worth deploying this kind of infrastructure to begin with, that and testing. So if that's your case, that is to look at containerized infrastructure right now. If you have a different use case for Postgres, then you might be looking at containerized infrastructure later as more of the sort of underlying issues and limitations are resolved. So let's talk about the main thing that I came here to talk about, which is observability. So we're back to our quantum superposition of elephants. That is, we have an elephant that is both alive and dead. We don't know because we haven't opened the box. Now, administrators, by the way, how many of you are database administrators? At least part of the time? Yeah. Okay. How many are primarily developers? Oh, they're developers, okay. So, ops staff are used to running Postgres on a physical machine, sort of in the clear. We've got our elephant here, right? And if we want to know if the elephant is happy or healthy or not, we can just look at it, right? We can go check and say, hey, there's the Postgres process and the Postgres service. Things seem to be okay, right? We've got our monitoring or whatever. And that's a system that people have used for quite a while, although there are some issues with it. And when you actually put Postgres in a container where you can no longer shell in to check anything, it brings forward a number of problems in terms of how do I know what the status of Postgres is in that container. Now, the thing is, these problems aren't actually new. These are problems that existed before, but we were used to relatively clumsy but acceptable workarounds in order to how to deal with problems of Postgres observability. And like many other things that we've been doing in sort of your common stacks and open source stacks and infrastructure, containerization has forced us to solve problems that we have been punting on for a long time, including the problems of observability. So when we've sealed Postgres in a container, and we can no longer shell in, and we no longer have a process list to check for the Postgres processes, and we're limited to connecting with it via defined ports, et cetera, then suddenly we need to actually add a monitor to the Postgres service itself, starting with something that tells us is it alive or dead, right? And there's a bunch of different ways to do that. One of the ones that comes built into most orchestration systems is what's known as the health check. This is from OpenShift. In OpenShift, it's called the Readiness Probe. A Readiness Probe checks all the time whether or not your service is still running, et cetera. And so this runs from the current orchestration master, and it's checking all the time that Postgres here. And all you can see, all it's doing is it's doing a PSQL, once per second to find out whether or not Postgres is still around on that particular node. Anybody run into any of the problems with centralized health checks? What was that? Yeah. One of the questions is whether or not the connection is available, right? Because just because the orchestration master can't connect to Postgres doesn't mean it isn't running. It just means it can't connect. Plus there's some latency. Plus there's the whole polling issue because we're using a centralized service here. And this sort of thing is fine if we have 10 Postgres running, but if we have 1,000 Postgres running, then you start actually waiting on the polling resources from the central node itself. And the big thing is that we don't want to trigger something like a failover event if Postgres is still running, because we may have some kind of a network snafu where some of our services are still connecting to the old Postgres, and if we fail over to the new Postgres, then you're going to have lost data because you have two different write locations. So, not that we shouldn't have the health checks. We have the health checks there as a safety thing, but we really need, in order to eliminate this indeterminacy problem, in order to eliminate, because with our centralized polling, we still don't know whether the elephant is really alive or dead. We just know that we can't connect to it, right? We've gone up and we've knocked on the box from the outside, and the elephant isn't answering. But that doesn't mean that we know that the elephant is dead. He could be asleep. He could be angry with us for locking him in a box. He could be busy and unable to answer. So we need something better than centralized polling. And one of the answers here is that the elephant himself knows whether he's healthy or not. So rather than looking at a polling model, we look at a push model that says each elephant should tell us what his status is, or her status. So the idea here is that within the individual container or pod, the elephant should instead poll the orchestration system and update its status as frequently as it can. And if the elephant can't reach, if Postgres can't reach the orchestration system, then it shuts down, which means that the polling interval is the limitation of your inconsistency window. Now, this requires a consistent available source of truth, but fortunately, within these container orchestration platforms, we have a consistent available source of truth because every one of these depends on something that's known as a distributed consensus store, which is a high consistency, low throughput, multi-node database that allows us to say, hey, we're going to, all of our individual Postgres and all of our individual elephants are going to write to this consistent source of truth, tell it what the status of the individual elephant is, whether or not we're alive or dead, and we can trust that as information on whether or not we're alive or dead. Now, one of the projects I work on is this thing called Petroni. So, and this is the central sort of liveness logic from Petroni, the run cycle. You can find it in ha.py in the Petroni source. And this is the cluster where it checks its own health status within the individual Postgres running in the individual container, and then it updates the orchestration system and possibly a separate distributed configuration store with its current status as to, you know, how healthy it is, so that we can have a consistent picture of what's going on. And the reason why this is more consistent than pulling from the central thing is because, again, if we have had a loss of communication, instead of Postgres keeping happily running thinking that it's still okay, if we have a loss of communication, the individual Postgres pod shuts down so that it cannot continue to receive writes when it is not part of the orchestration system anymore. So let's talk a little bit more about what goes into observability for Postgres. Now, part of the container orchestration world has come in as this thing called microservices, right? Is we're taking all of our services and dividing them up into these microservices that do as little as possible and then those microservices. And one of the lovely things about microservices is, honestly, the only check that you need on them is alive or dead. Are they responding or not, right? If you have a service that all it does is serve up a single web page, then either it's serving that web page or it's not. There aren't gradations. But a transactional database like Postgres is a little bit more complicated than that. Postgres can actually have multiple states, not limited to just alive, responding, or not responding. And we have to be aware of some of these multiple states because the actions that our infrastructure and that our system takes, depending on the multiple, can depend on a lot of the nuances of the multiple states. So I'm going to go through a lot of them. So let's go through a bunch of the other things that we might need to know about in terms of Postgres' health and status on an individual system. Things that go beyond just, are we alive or are we dead? So, I mean, obviously the first one is alive, healthy, responding to requests, running. That's pretty clear, right? Not complicated there. It's what we want most of our Postgres nodes to be doing most of the time. But what about this one? Alive but can't accept new connections. So within an orchestration system with automated failover, how do you want to treat alive but can't accept new connections? Anybody have an opinion on this? Okay, you say you want to treat it as dead. Yeah. Disagreement, yeah. The majority says treat it as live. And the answer there is that if you have a particular pod that has too many connections on it, and you fail over that pod and kill it, then all you're doing is failing over the too many connections. And the new pod in the new location will also have too many connections. And eventually you'll run through a whole failover chain until you eventually have a problem with the orchestration system or run out of nodes, whichever comes first. Now, however, if you have written a custom autoscaler for something like Kubernetes, then you actually do want to treat this differently from just alive. You want to say, hey, one of the things I'm autoscaling on is connections. If I go over 100 connections on any new node, bring up a new replica. Something you can do that's not available out of the box in Kubernetes, but they have this autoscaler API, and you can write your own custom autoscaler that has whatever criteria. So you add in a check that says how many connections does Postgres currently have. Anytime an individual node goes over X connections, you should spin up new replicas up to the number of physical nodes that you have. It's always the limitation of autoscaling is that you can't autoscale beyond your physical resources. So let's take another one. What about Postgres is running, but it's in recovery mode? Let it run. Yeah, this is mostly alive. Except we need to time it out at some point, right? If it's still in recovery mode, and the problem is that this then becomes administrator discretion, right? You say, oh, well, if it's still in recovery mode, after 10 minutes, then it's dead. Well, except if you have a 6 terabyte database, then being in recovery mode after 10 minutes is perfectly understandable, right? And so that's going to be a configuration setting that says, okay, how long do we get to run in recovery mode? How about alive but out of resources? So not connections full, but just I'm so slammed on memory and or CPU that I can't really respond to your requests, even though I'm listening on 5432. Autoscaling is one of the answers. Yeah. This one's a little indeterminate. And the reason why it's indeterminate, right, is that sort of autoscaling question, right? On the one hand, if I have a fixed amount of physical resources, then I actually want to treat this as live because failing over gains me nothing, right? Because if I fail over to a new machine, then the new machine will just be overloaded. And particularly if I've taken Postgres off a machine in which there was only one Postgres and failed it over to another machine where there are multiple Postgres, I've actually made the situation worse, right, by having a smaller number of nodes that are considered available and the same amount of traffic. On the other hand, you know, this runs into sort of overall system health in that, number one, if you have the ability to physically auto-scale, like you're on a public cloud, and you can actually add new public cloud nodes to gain extra hardware resources at the cost of money, or if there is potentially something wrong with that individual node in terms of its physical resource availability. And so this becomes a hard thing to automate, the live but out of resources situation, because you start getting into a whole if-then tree, which is far more than you want in the sort of state machine logic that you want for auto failover. So most of the time, at least so far, I end up treating this as, you know, the code that I have, I end up treating this as live. And the out of resources situation has to be dealt with by the administrator. Now here's one. Postgres is live. It's listening in port 5432. It's accepting requests, but replication is not working. Is this live or dead? Either way, stand by or master. Opinions? Your opinion's live? Yeah? It depends on whether you have infrastructure repair or replication. Yeah, my answer here is this is dead. And here's the reason. We're running in a cloud. All Postgres in a cloud needs to be replicated. Because if a Postgres is running in only one location, it's running for effectively a limited time. You know, sooner or later, something is going to happen to that location. If nothing else, the orchestrator is going to decide that that particular node is overloaded and it wants to migrate some stuff. And if replication isn't working, you can't migrate anything. It's locked up. And therefore, replication working is a required part of PostgreSQL working. This actually becomes a problem in observability. So there's a whole bunch of other things, a whole bunch of other meters. Postgres ends up becoming a control panel here. A whole bunch of other meters that we really need to know, things we need to know about Postgres in order to sort of check Postgres health en masse, right? Number of connections per node is an easy one, particularly if you're going to engineering kind of auto-scaling thing. Replication status, as mentioned. Archive backup status, right? Because you need to know whether or not backups are working in general for long-term storage or multi-location failover. What the current configuration of your nodes is in terms of database configuration. Why is that something that you need to know? Well, periodically you're going to update that configuration. You're going to do rollouts of a new configuration. And when you do rollouts of a new configuration, you have to have a way to check that you have in fact rolled out and replaced the old configuration. And then the complicated issue of performance. That is, how are my individual nodes performing? So now, Postgres has actually done a lot recently to expose a lot of this information over ports, which is the critical thing for containerized Postgres, because, again, a container, again, I'm not going to shell in. If it's not available on a port, I can't see it. So we've had PG settings forever for the general variable configuration. We've now added system views that view the HBA table, that view the post-PG config, so you know how that particular instance of Postgres was built. Number of connections in various permutations. Replication status from the master is something that we've had for a long time. We have a way to check archiving status now, a command for checking archiving status. So we can get a lot of that. Not everything is exposed, though. For example, while we can check the status of replication, we can't really check, particularly from replicas, from binary replicas, we have no way to check their replication configuration, except, you know, by shelling in. Because we can't see their primary connection information. If they are unable to connect to the master, that information is only available through the Postgres log. So again, this sort of, you know, log message issue, a whole bunch of things that write only Postgres log. And then we have the other issues of failure conditions, that we need information from, that we need debugging information from, but Postgres isn't running, like startup or recovery failure. How do we get information from that? Because, obviously if something hasn't recovered, it's a dead node, but we want to know why it's dead, particularly if we keep trying to start this Postgres instance on different nodes in our cloud and it keeps failing, then we need to know why it's failing. We can't just leave the orchestration system to keep trying to start it forever because it doesn't do us any good. So one of the ways to handle this is to have a daemon or some other controller expose all of the things that Postgres has not already exposed as REST, plus all the things that are available through port 5432, because it turns out that these orchestration systems and the new monitoring tools all expect to be able to access RESTful services. Now, something we can run as a query on Postgres is really easy to expose as a RESTful service. Other things we can actually have a daemon that looks at, say, Postgres' files and exposes information as REST to say, hey, we're going to have something wherever we make a REST request that will return the last 100 lines of the log, for example. The log is actually kind of a special issue, or that will return the recovery.conf information as JSON. Now, I didn't mention logs. So logs are actually a particular problem issue for Postgres, because how many times have you asked, where do I find this particular information about something about Postgres? Like, how do I find information about, archiving failing? What error message is getting archiving failing? Well, it's in the activity log. Right, you get that a lot? And it's in the activity log is a great answer for a single Postgres system running on a single server. It's a terrible answer when you're running 1,000 Postgreses in 1,000 different containers distributed across some physical cloud infrastructure. But we have information that appears only in the Postgres logs. By default, like actually, if anybody's used the one of the lovely things, there's the official Postgres image for Docker on Docker Hub. Do you know what it does with the Postgres activity log? What? No, actually it's going to dev null. They're literally just throwing it away. So sometimes the logs just get lost. There's also, the current, I think, the current mainstream OpenShift one writes it to the file system inside the container, which is useful to who, I don't know, because you can't actually access that. And so the alternative here is that people run log management services, right? You say have everything export to the systemd log, and then you collect the systemd log for all the systems, and you run log stash or InfluxDB or something else to collect logs from all of your containers. Now, this way at least the logs aren't lost and they're available in some form that is theoretically searchable. But there's some drawbacks to that as an information system. First of all, you're talking about getting all of the logs from all of your Postgreses, plus probably from all of your other services, where if you want to say, hey, the Postgres for this particular application keeps refusing to deploy, I want to know why, it's very hard to pull out that particular piece of information. It requires using, like I think the default in Kubernetes, if you install all the log tools that are available as Kubernetes examples from the standard Kubernetes Ansible, then what you get is a combination of InfluxDB and Elasticsearch, right? So you're now running a full-text search system in order to find that log message. So that's a problem. The bigger problem is, again, I'm looking at this from the perspective of automation. I'm looking at this from the perspective of how do I know what my Postgreses as a cloud are doing? And searching the logs via full text search is not something that you want to make part of a synchronous polling system, right? You don't know how long the searches are going to take. You don't know if they're going to return things that are not actually responsive to what you want to know. So this is still an ongoing problem with Postgres, and we need to actually do more work in terms of taking some things that are currently available only in the logs and exposing them elsewhere. In the meantime, some workarounds that I've been experimenting with. Obviously one of the things is you can actually pervert Postgres foreign data wrappers to expose the logs as a table. Not very performant, but it works. Another one that you can do is you can have, if you have a daemon like I have running for Petroni, and you've got the daemon running, the daemon can tail the logs, so you always have a little bit of log information available through the daemon. Obviously, you get log management tools. One of the things I haven't quite finished and experimenting with is one of the things that got added to Postgres 9.0, I think, somewhere around that era, are logging hooks. We actually have a C API for the log where you can actually redirect where the log goes. And so I've been looking at what would be a reasonable set where I could actually send, not just send the log to particular, expose it to particular locations that would be available over a port, but send different kinds of log information to different locations, right? Because for monitoring, I'm concerned about things like archive failure, like replication failure, like that sort of thing. I'm a lot less concerned about this query errored out, right? That can go to the log system. That can go to the log search system, right? What I need to know synchronously is replication failing, and if so, with what error message? But the other thing that people use logs for is performance analysis. So now, obviously, you can centralize your logs. You can send them out to a log search system. You can dump them out. You can use performance analysis tools on them. But I also want to know performance in sort of real time. I want to actually sort of look at synchronous performance, et cetera. And so one of the things that I've been bundling up, and I don't have it available for public consumption yet, is, are people here familiar with POWA? Anybody? OK, one person. It's a nice tool from Dalabo. It's a French Postgres company. And this makes heavy use of pgstat statements and a bunch of other optional Postgres extensions that collect performance information in order to display ongoing performance monitors of how Postgres is performing. And this works very well with a sort of cloud approach to give you an idea of what the sort of performance thing is in an instant-on perspective rather than log digestion, which is how we're used to looking at performance. And importantly, in Kubernetes, I have a pod. A pod has multiple containers, and so I just create a sidecar container that has POWA in it. I can even have that WebSocket activated so it's not running if I don't look at it, and ship that. And so each Postgres instance that I deploy automatically has this POWA interface for any time that I want to look at performance for the individual Postgres instances. Then later on, I need to figure out a way to collectivize that. But now, this is all in a little bit of a state of chaos right now. I'd hope to be a little bit further along with it with this conference. A lot of this comes out of my work with Red Hat OpenShift.io, which is Red Hat's CI/CD system for Java and other enterprise development, which is a little bit behind schedule. So it's still an ongoing work, and it's not like until after we're done with what we're doing on that I'm going to feel comfortable open sourcing it. The other thing is that instead of spending the summer writing code, this is what I spent most of my summer doing. That is in physical therapy because of an injury. So I've had a lot less time to develop. But some of the core of this is already there. For those of you who are not familiar with, people familiar with Petroni? Yeah. So some of the stuff exposing a bunch of the Postgres status information is already there in current versions of Petroni. It's all exposed over port 8001. And I'm working on exposing more information through the Petroni interface so that everything is available via a RESTful interface on the individual Postgres nodes. So, questions? Yeah, no, you actually want, I mean, part of it depends on what your sort of DR picture looks like. Usually you do actually want some form of archival backup because you always have the issue of, like, say you're on AWS, you have the potential for, say, AWS region failure. And archival backups to S3 can be a good way to recover from that. And again, the main way to deal with that, like in that case, is making sure that your archiving information is exposed, right? So you need to know if archiving is working or if it's failing. And that needs to be exposed over a port, not just in the Postgres logs. So we've actually got that information available via a system function in Postgres now, and so one of the things I need to do is actually expose that over a REST port through Patroni. Yeah. Yeah. So the question was why you should use stateful sets, and let me bring something up for that. So, is that, no, that is not stateful sets. So many windows. Okay. So stateful sets is a set of is actually a set of features we've been adding to Kubernetes, specifically to handle services which need various forms of persistence. And this particularly transactional databases, right? Because transactional database has all of the different forms of persistence there is, right? We need persistent storage, we need persistent identity, we need persistence of connection information. And so stateful set is the way to handle that within Kubernetes, because stateful set, if we're going to deploy, say, 3 Postgres instances in a Postgres cluster, that is initially a master and 2 replicas, then Kubernetes keeps track of, we've got, you know, Postgres 1, 2, 3. Kubernetes keeps track of 1, 2, 3. And if we lose one of those, if we lose number 2, it's specifically replacing number 2, which is important because, say, if you've lost number 2 because you've lost the kubelet, you've lost the individual node running it, but you haven't lost the persistent storage because it's part of cloud storage, then it will actually recover that storage. And alternately, if we are rescheduling a Postgres node on a machine where there was a previous Postgres node, it will not pick up the storage for a different Postgres node. So these are both important things that are not part of the non-stateful service, right? Because for a non-stateful service, if you define a persistent volume, the persistent volume has a name, and Kubernetes makes the assumption that it is transferable, which is not true for individual Postgres instances, right? I don't want to, even if it's a replica of the same one, I don't want to swap instances by accident. So, and the other important thing that stateful set does is it gives me the ability to route requests to individual Postgres nodes while still keeping this idea of the whole Postgres cluster as a single service. So I can both say, hey, I'm going to write to Postgres, or I can say I'm going to write to Postgres number 2. And both of those are available as calls, which is, again, not in the non-stateful sets where everything is load balanced. So more questions? Okay, well, thank you very much.